Hello viewers, in the last few programs we have discussed in detail the power electronic components and their use. We have checked their testing both physically and electrically, and we have also used CRO for testing those components. Now for further few programs we are going to see the characteristics of some of the important thyristor family members. To begin with, in this program I am going to discuss with you the VI characteristic of an SCR. Now for that I have a setup here which can be demonstrated for verifying the VI characteristic of an SCR. But before we take up the experiment, let us try to understand what is the VI characteristic of an SCR. You all know that an SCR is a 4-layer semiconductor device, and we can draw the layer diagram like this: P, N, P and N. So how many junctions are there? Of course there are 3 junctions, 1, 2, 3, and we name them as J1, J2, J3, and there are 3 terminals coming out like this. The first terminal which comes out, the P layer, is known as the anode. The second one which comes out of N layer is cathode, and the third one again from P layer is known as the gate. So you know that P layer has positive holes as majority charge carriers and minority charge carriers as electrons, and this N layer has electrons as majority charge carriers and the positive holes as minority charge carriers. Now let us see what happens to this device if I give a supply to it like this. If I connect it like this, that the positive of the supply is connected to the P layer and negative is connected to the negative layer, that is anode and cathode have been supplied with positive and negative respectively. In that case, because this has positive here, negative here, again positive here, negative here, so positive has been connected to positive, negative has been connected to negative. If I see the position of junction J1, this becomes forward biased. How? I will repeat, the positive of this junction has been connected to the positive of the supply and negative has been connected to the negative of the supply. So I say that junction J1 is forward biased. Now let us see junction J3 first. I will come later to J2. J3, you see, negative is connected to negative and positive is connected to positive, so J3 is also forward biased. Now how about J2? Let us see it. J2, you have negative here, and the negative is connected to positive of the supply, and positive here, the positive is connected to the negative of the supply, so it is reverse biased. Now here J1 is forward biased, which is nothing but a PN diode, forward biased, so no problem, conduction will take place. Here also J3 is forward biased, it is also a PN diode, so conduction will again take place. But how about J2? You concentrate, J2 is reverse biased and it is also an NP diode, so there is a problem here and the conduction will not take place. That means when I give a forward bias in this position, the device SCR is not going to conduct. Now let us see if I give a reverse bias to it. Reverse bias means I will just change its supply terminals and it will be like this. Here I will connect negative and here I will connect the positive terminal, negative and positive. Now negative is given to positive and positive is given to negative, so it is reverse biased. Now let us check the junctions. J1 you will find that it is now reverse biased, J3 is also reverse biased, but J2 is forward biased. Now if I compare this reverse bias condition with the earlier one, that is forward biased, I will find that here two junctions J1 and J3 are reverse biased and only one junction, that is J2, is forward biased, whereas in earlier case J1 and J3 were forward biased and J2 was reverse biased. So it is a worst condition. So if I reverse bias it, there is no condition, there is no cause that this device is going to conduct. Now I will come back to the forward bias condition like this. Again I will come back to the forward bias condition and let us see what happens. It is said that this is not going to conduct. Now why does it not conduct? It is because of this J2 which is reverse biased. What is happening here is, across this J2 a layer is being formed and this layer is known as depletion layer. In this depletion layer you will find the charges are there, but those charges are not mobile. Earlier case you have positive holes and electrons, but they were mobile charges, mobile, and they were charge carriers. But in this case, in the depletion layer you will have positive and negative charges, they are shown like this, but these charges are non-mobile or immobile, you can say, immobile. And this is because of this reason, that the charges are immobile, there is no conduction taking place in this depletion layer, and hence the device as such is not conducting. That means if I can destroy this depletion layer by some method, we can make this device conduct. Let us see, and the method by which you are going to destroy this depletion layer will be known as the triggering of the device. Let us see. This has been seen and proved that if this supply voltage is increased, this depletion layer width of the depletion layer, WW we can say, this is the width of the depletion layer, this is inversely proportional to the voltage applied. So if I give a variable supply here and if I increase this voltage, you will find that as you increase the voltage, the width of this depletion layer is going to decrease. At a particular voltage, this width will become 0. That means the depletion layer will be destroyed totally, J2 will have no existence at all, and in this case the device will start conducting. Since we have done it with the help of voltage, it is known as voltage triggering. That means the conduction has taken place because of the voltage applied here, and we call it voltage triggering process. Now there is another method of doing it, that is known as thermal triggering. Thermal triggering. Let us see what is that thermal triggering. In case of thermal triggering, it is seen that if you increase the temperature of this junction, the width of the depletion layer will again decrease. Now that means the width of the depletion layer is again inversely proportional to the value of the temperature. Now you can increase the temperature to such a value that this width becomes 0, and at that moment again the device will start conducting. So that method of triggering the device will be known as thermal triggering. But both of these methods are not very popular, because you see the voltage triggering, we are increasing the voltage and we have to go to a very high voltage, say 600 volts or 800 volts, and at that particular voltage this device is going to conduct, and doing it at that high voltage has no meaning. Similarly, thermal triggering is also not very relevant practically. If you know that this device is very small, it is a very miniature device, and at that junction J2 is also very small, it is a very small thing, and it is very difficult to increase the temperature of that particular junction. So both these methods, the voltage triggering and the thermal triggering, are not practically feasible. Now there is another very popular method of triggering the device, which is known as gate triggering. Gate triggering. Now you see the third terminal is gate here, and if I give a supply here, and that should be positive with respect to cathode. That means if it is positive with respect to cathode, what will happen? You are increasing the positive charge carriers here in this layer, and with that what will happen is you are going to generate electron and positive hole pairs. That whole electron pair generation will take place, and that will help to diffuse the current, and the current starts flowing from this junction further, and that will help conduct of the device. Now what happens is that without going to the voltage so high, we can conduct the device. The one thing, the voltage at which this started conducting here was known as VBO. We call it VBOF, which is breakover voltage, of course, forward. So the breakover voltage forward may be 600 volts, 700 volts or 800 volts, but without going up to that, with the help of gate triggering, we can trigger the device even at a lower voltage, say supply voltage of 220 volts or even lesser than that. That is why the gate triggering has its importance. It is very relevant that lesser voltage also, without reaching this VBOF, the device will start conducting. And almost all the circuits, whether you do it in experiments or commercial circuits also, this is the process which is being used. Now let us see the characteristic of this device, that is SCR, and how does it look like. If I draw like this is of course voltage, this is current. You will find that at the starting there is no current flowing, and the characteristic is something like this. This is the point where the device has started conducting, and it is known as the breakover voltage forward. Of course, this is the first quadrant characteristic and forward biased condition. Okay. Now if I go reverse biased, what will happen? Reverse bias also will go like this, and suddenly there will be a very high inrush of current at this point, and this point is known as VBDR, means reverse breakdown voltage. Now there is a meaning here, breakdown. What happens here is, firstly there will be very less amount of current, suddenly there will be very high inrush of current, and due to that high inrush of current the device will be damaged, and that is why we call it breakdown. That is means it is very clear that we are going to rule out this third quadrant, of course, of characteristic, and we are not interested in it, because you can see it and you will see that the device is going to be damaged. So we are not interested in the reverse bias condition, we are only interested in the forward bias condition, and the characteristic will be obtained like this. Here what is happening is, from this point to this point there is a little bit of current flowing. If you find out, very small amount of current is flowing up to this point, which is in milliamperes, and this current will not be able to conduct the device, and this current is known as leakage current. Leakage current. This current will not be able to conduct the device. At this point, which is VBOF, of course, there is certain inrush of the current and the device starts conducting. That means you can conclude that up to this point it is off state, and here it is on state. What does it mean? If you compare it with a switch, it is basically a switch, power switch of course, that it either has a state which is off state or it has an on state. So this is the characteristic which we are going to see experimentally here. Of course we are not interested in this, and we are not bothered about this also. So forward biased, that means the device is basically a rectifier, it is a switch which has two states, one is the off state, the other one is the on state. This is we are going to demonstrate with the help of this experimental setup which I have got for you to demonstrate. Okay. Now let us see the experimentation part. In this board we have rigged up a very simple circuit for the verification of the VI characteristic of SCR. Let us see, this is the SCR which has three terminals, the anode, the cathode and the gate. Across the anode and cathode, you see there is a voltage supply, and the voltage is variable in nature, 0 to 35 volt. This is obtained by this power supply. So, we can vary the voltage from 0 to 35 volts. Now, there is another power supply here. You can find that this power supply is feeding this point, which is nothing but the gate of the device, and the voltage here is constant 10 volts. With the help of this regulator, we are going to change the gate current. When we change the gate current, the device will start conducting at a particular point. Now, this resistor, which is a 5 ohm 5 volt resistor, is acting as a load resistor. These two terminals, you see there is an ammeter connected with this multimeter. This is being used as an ammeter, and it will show the current through the device. These two terminals, this is positive and this is negative. Across these two terminals, we are going to use this multimeter as a voltmeter, and it will show the voltage between anode and cathode. Across these two terminals, you see this is the positive, this is the negative. Again we are going to connect a voltmeter, and that is through this multimeter. This is being used as a voltmeter and will be connected between these two terminals, and it will show the gate voltage. In these two terminals, you find this is positive, this is negative. We are going to connect this multimeter as an ammeter, and what will it show? Yes, it will show the gate current. Now, this is all about the circuit what we have rigged up for the verification of VI characteristic of SCR. So, now let us do the experiment, and first of all I am going to connect the multimeters. So, this is the multimeter which will be connected across anode and cathode. This will go at the positive terminal, the red one. This will go at the negative terminal. So, this multimeter is going to show you the anode cathode voltage. Now, the yellow one, the middle one, this I am going to connect for the gate voltage. So, the red one will go at the positive terminal, the blue one will go at the negative terminal, and this ammeter, which is also a multimeter, but it is used as ammeter, this will be connected between these two terminals, the red one at the positive terminal and the blue one at the negative terminal. The power supplies are already connected. The analog multimeter is also connected. Now, I am going to put on the power supplies. The power supplies are on. The first one, this one, which is being applied at the anode cathode terminals, I am going to give 5 volts. So, I have put it at 5 volts, and this one of course I am going to keep it at 10 volts. This is kept at 10 volts. That means 10 volts is being applied at the gate and 5 volts across anode and cathode. At this setup, I am going to see when the SCR is triggering. For that, I am going to use this potentiometer. Now, you will concentrate on this analog multimeter, because at the time of triggering this will show you a kick. You see, I am increasing. Of course, you can also see, yet it has not triggered. This is the multimeter, which is an ammeter. It is showing 0.1 milliampere, that is the gate current. This is the gate voltage, it is about 0.73 volts, and this is the voltage applied between anode and cathode. So, I am again going to change it, and you concentrate on the analog black multimeter, analog 1. Here, you see this has given you a kick. What does it show? It shows that this particular SCR has triggered. And now let us see the values. The maximum current, it has gone up to 650 milliamperes. 650 milliamperes is the current. I would note it down, 650 milliamperes. Now let us take these readings. The gate current is 3.9 milliamperes. The gate voltage is about 0.88 volts. In this multimeter, you see the reading has gone down to 1.033 or so, which is approximately 1 volt, and this means that the device has triggered. One thing more is clear here, that when the device has triggered, the voltage across the anode and cathode is very less. And now you see, if I see this part of the experiment, this is about 650 milliamperes, this point is defined, this is 5 volts, and correspondingly this current is, this point is also known to you. This is origin. So this point is known, this point is known, this point is known, and this is of course origin. If I can get some of these points here, I can plot this part of the characteristic and I can join them and get the whole characteristic, which is forward biased. Of course, the reverse biased is not, I am not interested, it is not used. So we are only used for the forward biased condition, and which is the first quadrant characteristic of the SCR. So let us see, for that I am going to make it 0 volts. Okay? The 10 volts is of course constant, this is 0, and I am not going to disturb this regulator. And now I will increase this voltage in steps and we will see what is the value of the current. We will take down those voltage and currents and then plot the characteristic. So first of all, I may use my specs, I think. Yes, it is more comfortable now. I am going to keep it at 1 volt first. So this is 1 volt and the corresponding current is about 50 milliamperes, because this is 100, 200, 300, 400, it is 50 milliamperes. I will note down voltage, current of course milliampere, 1, 50. Then I make it 2 volts. Okay, this is 2 volts and this current has gone to 200 milliamperes. 2 is 200. Then I still go to 3 volts. I further go and I make it 3 volts and the current is 1, 2, 3, 350 milliamperes. 3 is 350. Then I make it say 4 volts. It has gone to 525 milliamperes. 525, 4 volts. Let us see what is the position of this multimeter. It has not yet conducted, because you remember at the time of conduction this will become 1 volt. Okay? So it has not yet triggered. So I increase it still and I make it 5 volts. 5 volts, it is about 700, it is little less than 700, say 675 milliamperes. 5 volt, and it has of course conducted at this point. If you note down the multimeter reading here, so it has conducted. So I will take up only those 4 readings, and at 5 volts it has already conducted and it is 675 milliamperes. Okay, 675 milliamperes. So what are the readings here? I'll make it 0. I'll write it down for you. Okay, so this is voltage, this is current, of course milliamperes. 1 volt is 50, 2 is 200 milliamperes, 3 is 350 milliamperes, 4 is 525 milliamperes. Okay, and after that you remembered at 5 volt it was the device had triggered. So we take up these 4 readings only, and if I plot them, you see I can get these points here, here, here and so on, and I can plot this part of the characteristic. This point is known to you, this point is known to you, this point is known to you, and this point is also known to you, which is the maximum value, and I can join them and draw this characteristic. Now this is one set of reading. Okay, I can take up another set by changing it to say 6 volts, then 7 volts, 8 volts, 10 volts, 15 volts and so on. You see, then of course this was disturbed because this has already triggered. For that I will make it 0 and then make it say 6 volt, then 8 volt, 8 volts, 10 volts, 15 volts and so on, and then take up another set of reading. So for different set of voltages applied at these 2 points, we will take up different readings, and finally we can draw these characteristics, different sets of such characteristics, which will verify the VI characteristic. At every stage you will find that the shape of the characteristic will remain the same. Now, what do you confirm? What we have verified from this experiment? What we have verified from this experiment is, number one, the SCR is a unidirectional device. It will only conduct in the forward bias condition, it will not conduct in the reverse bias condition. Okay? We get a characteristic like this. The forward bias will be like this. We join these points something like this, and this is ruled out. So, this part of the characteristic is obtained. So, this is one point we have verified. The second point what we have verified is the conduction of the device is regulated with the help of the gate current. We can trigger the device with the help of changing the gate current, and once we change the gate current, the device will conduct at different sets of voltage applied. Third thing what we have verified is that the characteristic of VI, the VI characteristic of the device can be plotted at different sets, but the shapes remain same. So, that on the whole verifies the VI characteristic of an SCR. Now, in the next program we are going to see the VI characteristic of another very important thyristor family member, which is diag. And you remember what is the difference between the two? Okay, let us not discuss it today here, we will discuss sometime later, and till then let us keep thinking. Thank you.